This is a copy of the lecture 21B, which had a problem with the audio. So I'm going to just narrate the audio along with this video. So we began the problem or the session with the problem 10.8 from the college physics book. So that problem says the wheel on a grinder is a homogeneous 0.9 kilogram disc with an 8 centimeter radius. So we want to translate that to mass equals 0.9 kilograms, radius equals 0.08 meters. Both of those pieces of information are there to help us find moment of inertia. And since it says it's a disc, that means that we have a constant of 1/2 in our moment of inertia formula. It then coasts uniformly to rest from 1400 RPMs in a time of 35 seconds. So this omega, 1400 RPMs, is revolutions per minute. We want to convert that directly into radians per second by getting rid of minutes. 1 minute equals 60 seconds, and getting rid of revolutions. 2 pi radians equals 1 revolution, and that will leave us with our omega initial in the proper units, 146.6 radians per second. Does this in a time of 35 seconds, coasting uniformly to rest. So omega final equals 0, and the time equals 35 seconds. How large a frictional torque slows its motion? So we're using net torque equals I alpha, where the presumption is that the torque that's responsible for the alpha, in this case, is just friction. So we have torque from friction equals 1/2 mr squared times, which is our moment of inertia formula, times alpha. Now we need to find alpha, so we will use our kinematic master equations. Since we know omega initial and omega final and t, we can find alpha, just rearranging, subtracting omega initial from both sides, and then we'll divide both sides by t. This gives us 0 minus 146.6 radians per second over 35 seconds. The total then is negative 4.19 radians per second squared. So we can take that value for alpha and plug it back in to solve for the torque. Putting all of our numbers in, torque of friction is 1/2 times 0.9 times 0.08 squared times negative 4.19, and the total value is negative 0.012 Newton meters. And we recognize that for torques it should be a force times a distance, so that's the easy way for us to find the units. Now we move on to college physics problem 10.11. In this problem we have a mass hanging from a frictionless pulley. We are not told that the pulley is a disc. Instead, we are asked to find the moment of inertia. So we have a 4 kilogram mass, and it is hanging. So when we draw our forces, it's got a force of gravity downward and a tension upward. And the wheel has a 15 centimeter radius, and the only force acting on it that creates a torque is the tension. So the tension is making the wheel turn in a clockwise fashion. And so when we talk about the signs of torque, the torque is coming from the tension. The alpha is going to give us A, and that's going to allow us to solve for the moment of inertia. But it tells us we need to find some other way to find both the tension and the acceleration. So we look at the mass m, and we use our kinematic master equations. And noting that we know delta x, t, and v initial is 0, taking the sign of delta x to be negative to be consistent with the direction that the wheel is rotating, clockwise being negative, to make sure the sign of alpha and A are consistent, we can use the first kinematic master equation. So that's our delta x equation. Noting that the initial equals 0, we can rearrange this and then we'll solve for the acceleration. So we have A equals delta x times 2 over t squared. When we plug our numbers in, we're going to get negative 0.095 meters per second squared. So that's acceleration A, but that will allow us to find the acceleration, angular acceleration alpha. So to solve for t, we look at the block and we just use sum of the forces in the y direction equals ma in the y direction. And keeping down negative to keep the consistency between a negative clockwise torque and negative alpha with a negative acceleration, we can rearrange and solve for the tension. Ultimately, tension equals m times the quantity a plus g, which is 3.88 newtons. Now, since we have the tension and the acceleration, we can go back into our net torque equation and plug these things in. So replacing the alpha with a over r and the torque with RT t sine of theta t, noting the minus sign because it's going clockwise. And our acceleration is negative, so those signs are consistent. We can rearrange, solving this for the moment of inertia. So we're going to multiply both sides by r and divide by a. So plugging our numbers in for the moment of inertia, we get negative 0.15 meters squared times 3.88 newtons times the sine of 90, because we have a right angle between the tension and the radius of the wheel of the pulley. And then we are going to divide that by our acceleration, negative 0.095, and that gives us 0.919 meters squared times kilograms, which, if we look at the normal formula for moment of inertia, sum constant times mr squared, we see we should have units of kilograms times units of meters squared. So those are the last two problems for rotational motion. And we basically moved on to talk about, set up the next chapter, which is on fluids, just to learn some notation and units. So first of all, the definition of fluids is liquids and gases. Anything that flows is a fluid. So contrary to popular belief, it's not just liquids, but it includes gases. And we discussed how we're going to take all of the variables, all of the physics that we've been doing, and just try to reapply it to liquids and gases. So the key two variables that need adjustment are the mass and the force. So the mass of a body of water is not as important as the density of the fluid. So instead of mass, we use density. The density uses the symbol rho, which is a Greek character. It looks like a P with a little tail, but additionally it sometimes looks like a lowercase p with a little bit of a slant in print in some books. So that's defined as the mass over the volume. And I use a capital V, a bold V for volume, because we also will see velocities and we don't want to confuse our different V's. After that, we discuss force. And the force that water exerts on a boat depends less on the water and more on the size of the boat. But what the water does do that's in common to, say, all boats is provide a certain pressure. So instead of talking about forces, we want to talk about pressure, P. So here we use a capital P, and I know that's confusing because it looks a little bit like the lowercase p for momentum or the rho symbol for density, but just try to be careful there. Pressure is defined as force over area. And the units of pressure are, in the metric system, would be newtons per square meter, and those are known as pascals, abbreviated as PA for short. We don't want to use just P because it will be confused with the variable pressure. We talked about the size of the pressure units. In chemistry, they have this beautiful, simple unit called the atmosphere, which is just taking the normal pressure at sea level on sort of an average day and saying that that pressure is just 1 in those units. But the pascals that would be equivalent to 1 atmosphere is actually rather large, 101,000 more or less, 1.013 times 10 to the 5th pascals. It's a very large number, equivalent to roughly the weight of 10,000 kilograms on every square meter. Then we talked about units used in medicine or meteorology, millimeters of mercury. 760 millimeters of mercury, mmHg, is the same as 101,000 pascals or 1 atmosphere. In PSI, if we talk about tire pressure, the 1 atmosphere of pressure in PSI is 14.7 PSI. And one of the students volunteered that her tire pressure is 32 PSI, and that would be what's known as a gauge pressure, which measures the difference between the pressure inside the tire and outside the tire. And so the relationship between the gauge pressure and the absolute pressure, which is what we primarily will be talking about in this class, is that the gauge pressure is 1 atmosphere less than the absolute pressure. So for example, if you have if your gauge pressure is 32 psi, you would have to add 14.7 to that to find the absolute pressure of 46.7 psi. All right, that hopefully will fill in the audio gaps for this lecture. Thanks a lot.